The maximum likelihood estimation of the spatial error model proceeds very much along the same lines as the spatial lag model. So what I'm going to do is spell out the likelihood function, shows you what are the minor differences with the lag model, then show you what the asymptotic variance matrix looks like and a major difference with the lag model, and talk a little bit about residuals and fit. We mentioned that when we discussed the notebooks, how there's different notions of residuals, and some of them still have spatial autocorrelation and some don't. And that's basically what this is about. So the likelihood function is, again, going to be based on the point of departure, which is a multivariate normal distribution for the error terms. But before we go there, for the lag model, the estimation problem was one of endogeneity, of simultaneity. And we had to control for that. Either we controlled for it by spelling out the full likelihood function, or we controlled for it with instruments. Here, the problem is a little different. The problem is only concentrated in the variance for the error term. So the variance of the error term, we saw this way in the beginning when we talked about spatial processes. If you have a spatial autoregressive process in the error term, then the reduced form of that, it's really not a reduced form because they're all errors. You don't know, you can't see them. Takes on this form with this inverse matrix that we see all the time. And that gives us the variance matrix as this big inverse thing. And there's an important concept here, and that's a concept of a nuisance parameter. And a nuisance parameter is something that helps, even though it's called a nuisance, it helps in the estimation, but it's not necessarily of interest in its own right. So we can think of it as a parameter that helps us getting a better estimate for beta, better in the sense of a better representation of the precision of the estimation primarily. But if we don't care about lambda, then we don't need to do significance test or anything like that. So it's a problem of efficiency. It's a problem of estimating the variance covariance matrix. Remember in the very beginning, I said, if you really don't care about the parameter itself, you're not just as well, but in some circumstances, you might as well just do OLS and take hack standard errors. The hack standard errors correct for all kinds of different spatial autocorrelation. You don't have to specify a model. You don't have to estimate a parameter. All that stuff goes away. Now, the key issue, the key concept here is if you have a consistent estimate for lambda, irrespective of its precision, then you can use that to get a better estimate for beta. The logic that we'll see later with the generalized methods of moments is exactly that. We get a consistent estimate as a solution of equations and we plug it in. Where do we plug it in? We plug it in spatially weighted least squares. As you may remember, whenever the error terms do not have the sigma squared I variance covariance matrix, then you move from ordinary least squares to generalized least squares. And generalized least squares are a form of weighted least squares where the weights, as always, are the inverse variances. I mentioned this before. Why would you weight with the inverse variances? Because you want to favor the observations that have more precision. So the ones with the smaller variances, error term, means greater precision, mean you give them greater weight. The ones with the larger variance for the error term, less precision, you give them less weight. That's the whole idea of weighted least squares as opposed to ordinary least squares. Ordinary least squares, every observation gets the same weight. Weighted least squares, the more precise observations, so to speak, are favored. That's the principle. Now, this is where our luck comes in. If you look at this expression here, it includes the inverse of the variance matrix. Normally, that's a real problem, because this matrix is n by n. That's big, right? Now, luckily, our variance matrix is an inverse. So an inverse of an inverse gets rid of the inverse. So we never have to do an inverse of an n by n matrix. We only have to do an inverse of a k by k matrix, and we know how to do that. That's not a big problem. And if you do the math and work it out, this expression in the middle here, this sigma inverse, becomes a product of two filtering matrices. We call them filtering because they're the original variable, the identity matrix, I, minus a spatial lag weighted by this coefficient. So if you just look at this one for now, and you work out the multiplication, this is x minus lambda wx. So that's the difference between the original x, the average of the neighbors scaled by lambda. And that's called a spatial filter. You filter out the effect of the neighbors. In other words, this spatially weighted least squares boils down to an ordinary least squares of the spatially filtered x and the spatially filtered y. Of course, to get the spatially filtered x and y, you need to have lambda. Lambda is the nuisance parameter. Either you estimate lambda with everything else and you get standard errors and all that stuff, which is what the maximum likelihood approach does, or you get a consistent estimate for lambda using whichever method you can think of and plug it in and you're good to go. The price for that is that you don't get inference on lambda. But if you don't care about that, that's an easy price to pay. Right? So this spatially weighted least squares, Collegian and Prucha call this spatial Cochrane-Orcutt. Cochrane-Orcutt is a time series concept where you create first differences in time and run the regression on that. So in time series, this would be yt minus rho yt minus 1. Here, it's not that easy because we don't have a specified definition of a neighbor, and instead we use this concept of a spatially lagged variable, which in essence is an average of the values at the neighboring locations. Okay, maximum likelihood, same thing. We start with the error terms. We set up a multivariate normal distribution. We get the likelihood, which is joint for everything. We can't do the product of the individual likelihoods or the sum of the individual log likelihoods because of the correlation structure. So we have to throw the whole thing in with the full variance covariance matrix, first order conditions, second order conditions, and we're in business. As I said, I'm going to go through this fairly quickly. It's based on a multivariate normal distribution. Again, it's the joint density, not the product or the sum of the logs. We have our friend the Jacobian again, now with lambda. In essence, this becomes a least squares in the spatially filtered error terms that we don't know, but with this additional Jacobian term. So it's not just straight least squares. We have to rescale it by the log of this determinant. So all the same computational problems we ran into for the lag model, we run into here as well. And so we'll do brute force, method full, just compute the determinant, or we do the ORD method, or we do the LU method, as we saw last week for the lag model. So what does this look like? It looks like a very complicated thing, but after some algebra, just like in the lag model, remember what we did in the lag model, we were able to spell out the solution for beta as a function of rho, the solution for sigma square as a function for rho. We plug that into the log likelihood, and that gives us a concentrated log likelihood with just one parameter. That's very easy to optimize. Here, it's ironically a little more complicated, but in the end, it's the same thing. So after some additional manipulations, you end up with a log likelihood that is concentrated in the sense that it's only a function of one parameter, lambda. So then it's a nonlinear function in lambda. We find the optimum. We find all that other good stuff, right? Inference. Inference is the inverse of the negative expected value of the second partial derivatives, the information matrix, right? So just like before, we have to get the second partial derivatives, figure out what the expected value is, take the inverse. However, unlike what holds for the lag model, remember in the lag model, it was not block diagonal between beta and rho. So we had all these kind of weird results that were non-standard. Here we don't have that. In other words, we can compute the variance-covariance matrix for the beta estimates just using the spatially filtered x's. There's lambda in there, but the precision of lambda doesn't matter. That's a big difference with the lag model, where the precision of rho did matter. This matrix has two blocks, one block for beta and one block for lambda and sigma square. And the block for lambda and sigma square is this, a lot of traces, a lot of complicated matrix expressions. If you don't want any inference, you don't bother with this, right? So a lot of the early estimation methods for this did not bother with this. They just maximize the log likelihood function and then did a likelihood ratio test on the parameter instead of a asymptotic t-test. Because the likelihood ratio test is easy to do. What you need is a maximized likelihood for the error model, the likelihood that corresponds to the least squares estimation, and you plug it in a likelihood ratio test. So that doesn't require any of these big fancy matrix traces and inverses and things like that. So in sum, it's block diagonal, which is a good thing. Lambda is a nuisance parameter. Consistency is all that matters. The precision of lambda does not affect the precision of the beta estimate. But the value does, because the value of lambda enters into this spatially filtered X, which is what we ultimately use to use the betas. So that's all good. Then a few comments about predicted values and residuals. Predicted value, unlike the lag model, there's no spatial multiplier. Why not? Because the error terms average out to 0. So when you try to find out what is the conditional expectation of y, conditional on the right-hand side, the error term is gone. So it's just x beta, just as least squares. So there's really no effect of having this error autocorrelation. The effect is on the variances, on the standard errors. And then there's this notion of somehow exploiting the covariance structure in the error terms. And this is used in spatial interpolation. Now, we don't really talk much about spatial interpolation because in our setup, there's nothing to interpolate. We have a spatially exhaustive data set. If you have all the counties in the US, what are you going to interpolate? There's nothing in between the counties. So that's the expanding domain asymptotics. But if you have infill asymptotics, that's all about interpolation. And then you can use this very old result due to Goldberger that creates an optimal unbiased predictor, a BLUP, which takes advantage of the structure of the variance covariance matrix. So the sigma inverse is in here. So that's for interpolation. You might say, well, why do we need this error model? It's a precision thing, and I'll be the first one to say this day and age, not nearly as much as we used to, because our data sets are larger. Of course, there is a difference, but if the difference happens 5 decimals after 0, you don't really care, right? If it's 0.00005 or 0.00004, you don't care. There is a difference, but the difference in practice is immaterial. Residuals, just like we saw for the lag model, depending on which one you use, if you take the regular residuals, the unfiltered residuals, they will still be spatially correlated. If you filter out the spatial correlation, they will not be spatially correlated, or they shouldn't be. If they are, something is wrong, right? So if you take, and we'll see this in the notebooks, just like in the lag model, we had 2 notions of predicted values and 2 notions of residuals. Here we have 1 notion of predicted values, but still 2 notions of residuals. One type of residuals will still have spatial correlation, the other type will not. It's been filtered out. And fit, just as before, R square is no good. We can do a pseudo R square, which is simply a squared correlation between observed and predicted. And we can do measures based on the log likelihood. As I mentioned the other day, as such, the log likelihood is not a measure of fit, but it's used as kind of a proxy for a measure of fit. The log likelihood is a probability. So the higher the joint probability, the better your model is. That's the rationale. And as we saw before, the AIC and SC, or BIC as it's sometimes called, they correct for differences in parameters. One thing that I've found is that different software packages don't always count lambda as a parameter. So it is debatable. It's a nuisance parameter. If you don't count it as a parameter, then there is no correction between, the correction for a standard regression and a spatial error regression will be the same. It's just K. If you take it into account as a parameter, it'll be K plus 1 for the spatial error model. Unlike the spatial lag model, where there's no discussion, it's always included. But a spatial error model, you have to look at the fine print, whether it's included or not.